Isaac Newton's famous work, the Principia, was first published in the year 1687. And this is the book in which his laws of motion and law of universal gravitation were first formally introduced. So we write the law of gravitation, says force is a vector that's equal to this universal constant times the mass of one object times the mass of a second object divided by the distance between the two squared, and to make the right side of the equation a vector quantity, as long as we multiply by a vector with a magnitude of 1, so this unit vector we call r hat, then both sides of the equation represent vector quantities. Now, I don't know exactly what the formula looks like in the Principia. I haven't seen that in a long time. But I can tell you this much. Newton himself did not really know the value of this constant. The idea that Newton expressed is that the force of gravity had to be proportional to the inverse of the distance squared between two objects, and at the same time, the force had to be directly proportional to both the mass number 1 and the mass number 2, and an equation of this form says that, right? So whether or not Isaac Newton called that constant G or wrote it as C, or possibly expressed it as K, doesn't make a difference. The idea is there has to be some constant of proportionality that corrects the equation, but the key variables are the masses and the distance. Well, enter Henry Cavendish, and in the year 1798, he performed a famous experiment that determined the value of the constant capital G, which we know as 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Here's the apparatus that he used. There was a torsion wire that hung and attached right at the middle of a well-balanced horizontal rod. And then at the ends of that rod were a couple of massive spheres, small masses. One small mass right there, another small mass here. Let me copy that again. A little mass there, a little mass here. The torsion wire and the horizontal rod. In a previous chapter, we introduced ratios of stress and strain. And suggested as long as you don't stress things too far, then the relationship between stress and strain is often linear. So some examples we saw were the stress-strain ratio known as Young's modulus. Another stress-strain ratio is just the K value in Hooke's law, and says F equals negative K delta X. In any case, if you make a graph of stress versus strain, there's a what do we call it? A proportional limit in which the ratio of stress to strain is linear. Beyond the proportional limit, you still stay within the elastic limit, but the graph no longer stays linear. If you go beyond the elastic limit, then you get into the plastic behavior of the material, and you eventually even reach a fracture point. So within the proportional limit, stress and strain are linear, and one type of stress is torsional stress. Which means, what if you tried to, well, let's draw this more three-dimensionally, right? Maybe the eyeball is looking down on it this way. So if we see it from that aspect, like that X is looking straight down the string that hangs at the center of the rod, if you were to push with a force in that direction on one of the masses, and then push with a force in the opposite direction on the other mass, both of those forces would tend to make this want to rotate in a counterclockwise direction. But then if you released it from rest, after it had rotated through some angle theta counterclockwise, there'd be a desire for the string to return to its equilibrium position and rotate back clockwise and return to the original orientation. So you could push with a known amount of force and see how far that causes the rod to rotate. And then you can increase the force even more and see how much farther it rotates, and so on, and create your own graph of torsional stress compared to strain. Then, instead of applying a known force directly with your fingers or some other instrument, you can place a large mass, capital M, near the small masses that are attached to the rod that we'll label as little m, and then the force that would want to make it rotate in a counterclockwise direction would just be the gravitational force of attraction between the masses. There'd be a small force right here that pulls little m toward big M. There'd be another small force right here that also attracts this little m toward this big M, and the rod would rotate in a counterclockwise direction. So here's the same idea pictured once again. The force is very, very small. We know this. It turns out that that gravitational constant is not a large number. It's a very small number, 6.67 times 10 to the negative 11th. The key is that the exponent is negative and very large, right? 0.000. We have to say a lot of zeros before we say 667. M1, M2 over r squared. So unless M1 or M2 is a mass that's as large as the Earth, then this force is relatively small. So even if these are heavy lead spheres, it's a pretty small force of interaction that causes the rod to twist. But it does twist a little bit nonetheless. Now you can exaggerate how much twist. You probably wouldn't see with the naked eye how much the rod twists, but if you put a little mirror at the center of the rod, and we're able to shine a beam of light onto that mirror. Oops, bad aim. And let's try that again. You shine a beam of light onto the mirror, and that beam of light will hit the mirror and reflect back and strike a wall somewhere off at a distance. If the rod rotates just the tiniest bit, then it causes that reflection to move just a little bit, and even if the angle is small, the displacement on the wall could be large as long as the wall is far enough away. And so now you know the value of the relationship of stress to strain because you produced the graph of stress to strain. So all you need to see is how much strain results from the unknown force, and you could work your way backwards to figure out how large that force must have been. If you know the value of little m and you know the value of big M, then the only quantity to have to solve for that remains would be the value of g. And so this is the nature of the Cavendish experiment. I have another video that you can watch after this one that shows another physics teacher doing his own investigation and attempting to reproduce the Cavendish experiment. So thanks for watching this video, and watch the next video I have that presents the Cavendish experiment another way.